Hello students, welcome to EPG Pathshala. I am Professor P.N. Kotru from Jammu. Today we are going to discuss about a module entitled Experimental Crystal Growth Part 2, that is the gel technique, under paper crystallography and crystal growth. So students, let us see what we are going to learn in this module. We are going to learn about gel technique of crystal growth. We will be discussing structure and properties of gel, the preparation of Hydro-silica Gel, mechanism involved in the gelling process, role of gel in the crystallization process, growth by chemical reaction, chemical reduction method, complex decomplexion method, and solubility reduction method. Details of some materials grown as crystals in the gel medium, growth mechanism in gel and nucleation control in gel method, various methods of crystal growth by gel encapsulation method, advantages, disadvantages and limitations of gel growth method, and we will have some examples of gel grown material. Gel technique of crystal growth. The gel technique of crystal growth is the most simple and versatile technique compared to other methods of crystal growth under ambient conditions. Since the method involves minimum technological sophistication, it has been exploited for the growth of useful crystals suitable for research and technology. Crystal growth in gel media yields well-faceted crystals in several cases which exhibit many crystallographic features. Gel growth has also provided opportunities for the experimentalists to conduct studies under microgravity conditions in spaceships. The method has gained attention owing to its suitability for growing crystals of biological macromolecules and in studies involving crystal deposition diseases in human beings. It was in 1896 that a German chemist Edward Lessing, who was a colloid chemist and a photographer, first observed the periodic precipitation phenomenon. Mechanism of the phenomenon of periodic precipitation of rings was described by German chemist Oswald at the end of 19th century. These discoveries led many investigators to concentrate their studies on colloids and observe this particular phenomenon. The idea of utilization of gel as a medium of crystal growth was put forward by Fisher and Simons in 1926. The art and science of growing crystals in gels remained largely dormant during the period 1930 to 1960. Henisch has described the technique of crystal growth in gels in his book Crystal Growth in Gels, and another book, Crystal Growth in Gels, is an intermediate process between growth from solid phases and growth from liquid solutions. The structure and properties of gel. The gel is defined as a highly viscous, two-component, semi-solid system, rich in liquid and having fine pores. These fine pores may allow the free passage of electrolytes and sustain nucleation. The gel medium works as a smart material that is sensitive to the minutest changes in the ambience. Gels are broadly divided into two, organic and inorganic. If water is in the place of liquid, it is called hydrogel. The various types of gels used in crystal growth experiments are Hydro-silica Gel, which is also known as sodium metasilicate, then agar-agar gel, carbohydrate polymer gelatin gel, which resembles protein structure, clay gel, soap fluid, polyacrylamide, hydroxide in water, olates, stearates, etc. The silica gel made out of sodium metasilicate is often used because of its easy availability and better performance in growing many crystal compounds. In some particular cases, organic gels are preferred, and the selection of gel depends entirely on the nature of the electrolytes involved. Preparation of hydro-silica gel. The water glass, that is sodium metasilicate powder, is dissolved in doubly distilled water, and by changing the hydrogen ion concentration, that is pH, of the solution, the desired gel can be prepared. The pH factor is an important parameter which determines the rate of polymerization and the speed of gel setting. For maintaining the acidity or the hydrogen ion concentration, an acid is requisite concentration is added to the system. During gelation, the pH of the mixture varies and the gelation period varies from few minutes to hours or days. For growing the crystals of good number of materials, the pH ranging from 3 to 6 are found suitable. Acid commonly used to acidify the gel are nitric acid, hydrochloric acid, tartaric acid, acetic acid, oxalic acid, selenous acid, etc. Fresh gels of pH ranging from 6 to 8 are highly transparent in nature. Gel aging is another parameter which is required to be monitored. The aging hardens the gel and decreases its transparency and easiness of diffusion. One of the most important factors affecting the hardness of the gel medium is its density. Dense gels produce poor quality crystals. On the other hand, gel of insufficient density takes a long time for formation and it is mechanically unstable. Range of densities in between 1.03 to 1.06 G per cc yield better results in many systems. The optimum density allows the growth of reasonably bigger crystals by this technique. The mechanism of gelling. Gels are two-phase systems comprising a porous solid with liquid-filled pores. The solid separating the pores is quite thin, typically less than 2 into 10 raised to power minus 6 mm. The size of the pores depends on concentration and pH of the gel. While the median dimensions of pure pores are about 0.2 micrometer in gels of high density, the dimensions of pores in dilute gels gets bigger, which may be taken as around as 2 micrometer. There is large spread of dimensions in gels. The ratio of maximum to minimum diameters of pores being a factor of about 10 to 50 or even more. The pore size can be manipulated by varying the growth parameters like gel density, concentrations of reactants, pH, and the surrounding temperature. Structures of many of the gels are complicated and still not fully understood. However, the structure and properties of the hydro-silica gel is described in great detail in the literature. It's worth noting that the hydro-silica gel is the polymerized form of silicic acid. When sodium metasilicate is dissolved in water, monosilicic acid is produced due to the reaction Na2SiO3 plus 3 times water gives H4SiO4 plus twice NaOH. This is a reversible process, and the byproduct, which is strong alkali, that's NaOH, remains in the solution. This is the reason that the solution remains alkaline. The monosalicylic acid liberates the hydroxyl ions and polymerizes as shown below. OH, SiOH, OH, OH plus OH, SiOH, OH, OH gives SiOH, OH, OH, SiOH, OH, OH plus H2O. This process continues till the entire molecule becomes part of the three-dimensional network. The oxygen-silicon linkage is extremely strong and which is irreversible. A section of the cross-linked polymer is shown in the diagram below. The byproduct resulting from the reaction is water, and it accumulates on top of the gel surface because it is lighter than the gel. This phenomenon is called syneresis. Much of the water has its origin in the above condensation process, and some may arise from purely mechanical factors connected with a small amount of gel shrinkage. The well-known stability of the silicon-oxygen bonds is responsible for the fact that the polymerization is largely irreversible. The period of gelation is controlled by pH value of the solution, though it is very difficult to control the total period of gelation precisely. In the above structure, H3SiO4 negative and H2SiO4 2 negative are also formed during the process of gelation. The relative abundance of these products depends on the pH value. When the pH is high, H2SiO4 2 negative ions are abundant and more active. The H3SiO4 negative is favored by low pH, and they are believed to be responsible for triggering the polymerization. In due course, cross linkages are formed between the chains, and these contribute to sharp increase of viscosity that is clearly visible in gelation. The first result of such a linking process would be the production of Sol particles, and the extent to which such particles then continue to associate to form macroscopic gel depend on their surface charge. The important feature of gel is its abundance of pores. The gel matrices contain fine pores having different dimensions. The pore is usually of the order of a micrometer in size. The pores may behave as capillary for the transport of ions. X-ray studies of silica gel show that it has close resemblance with silica glass, but with some inhomogeneities. Basics of gel technique. Gel technique is defined as a method in which two solutions of soluble salts are brought in contact by diffusion through gel. The precipitation of an insoluble phase within the gel results in subsequent nucleation followed by crystal growth. The gel performs the following role. 1. It limits the number of critical size nuclei formed in the medium. Number 2. It decreases the rate of growth by controlling the rate of diffusion of reacting ions and by governing the speed of reaction at the crystal growing surface. Number 3. It acts as a three-dimensional crucible, holding the crystal in space within the medium without exerting strain on the growing crystal. Crystallization process in gel medium. Based on the nature of the chemical reactions and physical changes involved during the growth processes, gel medium growth may be classified into 4 groups. Growth by chemical reaction, growth by chemical reduction, growth by complex dilution method, growth by solubility reduction method. Let us briefly describe each one of them. Growth by chemical reaction. The method can be taken as the basis of all methods of gel growth, and is actually a crystal growth by chemical reaction. The crystals, which are insoluble, are slightly soluble in water and decompose before reaching their melting points, can be grown by adopting this procedure. The basic requirements of using this method for the growth of crystals are: the reactants used must be soluble in the solvent, whereas the product crystal must be relatively less soluble. The gel must remain stable in the presence of reacting solutions and should not react with these solutions or with the product formed. Two aqueous solutions of soluble salts are appropriately selected and allowed to diffuse through the gel so that there is a slow and controlled segregation of ions and molecules, leading to formation of precipitate of an intermediate phase as a result of chemical reaction. The crystals grow out of the precipitate. The role of the gel is to limit the number of critical size nuclei and decrease the rate of crystal growth, either by controlling the diffusion of reacting ions or by governing the reaction velocity on the surfaces of the growing crystals. Resulting chemical reaction can be expressed as AX plus BY gives AY plus BX, where A and B are cations and X and Y are the anions. This can be achieved by using a single test tube as crystallizer, in which one of the reactants is incorporated in the gel known as lower reactant, and the other reactant is poured over the crystallizer known as the upper reactant, so as to allow its diffusion through the gel matrix. The two reactants are allowed to react by diffusion into an essentially inactive or non-reactive gel. There have been several innovations in the development of crystallization apparatus from time to time, as would be discussed in the relevant section. However, the basic crystallizers commonly used are shown in the schematic diagrams of figure 27.1. In one case, we have a single tube, and so is known as single tube technique. Here, one of the reactants is incorporated in the gel itself, while the other reactant is poured over the gel after allowing it to set and age for a specific period. Figure 27.1 is a schematic diagram showing single diffusion and double diffusion gel growth apparatus. The second type is a slightly modified one, in which the two reactants are allowed to react by diffusion into an essentially inactive gel. There are a variety of crystallization apparatus used for the growth of crystals based on other innovative techniques. The major problems associated with the growth apparatus described here are the depletion of one of the reactants inside the gel, the incorporation of reaction waste product in the growing crystal, supporting, handling, and cleaning of the crystallizers, and gel preparation inside the horizontal tube open at both the ends. In figure 27.2 is shown schematically an improved design in which attempt has been made to eliminate some of the above said problems and also facilitating the growth of mixed and doped crystals by multiple diffusion. Figure 27.2 is a schematic diagram showing modified crystallizer for gel growth. Chemical reduction method. The method is suitable for growing only metal crystals from gel media. In fact, Hatchak and Simons are the first to report the growth of gold crystals by adding 8% oxalic acid solution over a set gel containing gold chloride solution. By this particular method, crystals of nickel, cobalt, selenium, lead, and copper have been grown. Complex decomplexion method. In this method, chemical complex of the material, which is to be grown as crystal, is made with aqueous solutions of some suitable substance called complexing agent. The former is homogeneously mixed, and then such conditions are provided externally which are conducive to decomplexing or dissociation of the complex formed. A standard procedure adopted for decomplexion is to increase the dilution steadily while complex solution is diffused through the gel. Crystal growth by this method was first attempted by O'Connor et al. For the growth of cupric halide crystals. Solubility reduction method. This method is applicable to the growth of single crystals of highly water-soluble substances. The growth of ammonium dihydrogen phosphate, abbreviated as ADP, single crystals, by this method was first reported by Glocker and Soist. In this method, the substance to be grown is dissolved in water and then incorporated into the gel-forming solution. Then a solution which reduces the solubility of the substance is added over the set gel to induce crystallization, as in figure 27.3. For example, potassium hydrogen phosphate, abbreviated as KDP crystals, have been grown by adding ethyl alcohol over the gel containing a saturated solution of KDP. Crystals are grown due to reduction of solubility of KDP in the liquid phase by the diffusing alcohol. Figure 27.3 shows a schematic diagram illustrating another process of crystal growth by gel method. Examples of materials grown in gels. A large number of crystals have been grown by using the gel method of crystal growth. The list is quite large. However, some typical examples may be cited here in the following table 27.1. Table 27.1 has 5 columns. One column is giving the serial number. The second column is on first reactant. Third column is second reactant cum solution. The fourth is gel used, and the fifth is crystal grown. At serial number 1, AgI-HI complex, the first reactant. The second reactant is water. The gel used is sodium metasilicate, and the crystal grown is AgI. At serial number 2 is mercury chloride, in which the second reactant is potassium iodide. Gel used is sodium metasilicate, and the crystal grown is mercuric iodide. Serial number 3, the first reactant is calcium chloride. The second reactant used is tartaric acid. The gel used is sodium metasilicate. The crystal grown is calcium tartrate. At serial number 4 is AgNO3 is the first reactant. Second reactant used is sulfuric acid. Gel used is sodium metasilicate, and the crystal grown is Ag2SO4. At serial number 5, NH4CO3 is the first reactant. The second reactant used is CaCl2. The gel used is sodium metasilicate, and the crystal grown is calcite having chemical formula CaCO3. At serial number 6 is ytterbium nitrate. The first reactant is ytterbium nitrate. The second reactant is tartaric acid. The gel used is organic gel, that is agar-agar, wherein some few drops of HNO3 are added, and the crystal grown is ytterbium tartrate. At serial number 7, the first reactant used is holmium nitrate. The second reactant uses tartaric acid. In this, both gels are used, that is sodium metasilicate and the organic gel, which is agar-agar with few drops of HNO3. The crystal in using both the types of gels is holmium tartrate. At serial number 8 is gadolinium nitrate is the first reactant. The second reactant is tartaric acid. Again, here gel used are both sodium metasilicate and the organic gel, that is agar-agar, wherein some few drops of HNO3 are added. And the crystal grown by using these reactants is gadolinium tartrate. Then at serial number 9 is CuCl plus HCl as the first reactant. The second reactant is water. The gel used is sodium metasilicate and the crystal grown is CuCl. Growth mechanism in gel. The crystallization in the gel medium is the result of diffusion of the ions through it and their incorporation at the growing phase. It has already been said that the diffusion depends on several factors like pH, density, temperature, age, quality of the medium, and the impurity of the interacting components. To analyze the growth mechanism, it is necessary to take gel as a diffusion medium and the complete process of crystallization as diffusion-controlled phenomenon. Homogeneous nucleation is favored by gel in which supersaturation near the growing phase of the crystal in the gel medium is usually high enough for this. In the medium, the diffusion of the discharged matter is a consequence of the chaotic motion of the molecules. A molecule of an ion changes its place with a frequency tau raised to -1 equal to kb T upon h exponential of minus delta G upon kBT, which is referred in here as equation number 27.1, where delta G is the activation energy for transport of the molecules. It is equated to the energy required for the formation of a nucleus. The nucleation rate can be related to the mean free path lambda and the diffusion coefficient D as lambda equal to 2d tau raised to 1 by 2 or tau is equal to lambda square by 2d, which is referred as equation 27.2. Let us put lambda approximately equal to d, where d stands for ionic diameter. F will be equal to tau raised to -1, which will be equal to 2 capital D upon small d square. Using equation 27.1, we have small f equal to kb T upon h exponential of minus delta G over kBT, which is given as equation 27.3. Fick's law, in the case of one-dimensional diffusion, gives the rate of growth of the crystal in gel as capital R equal to capital D into V into C alpha minus Cs raised to 1 by 2, referred here as equation 27.4, where V is the speed at which the growth front is advancing. Since each particle is required to be treated separately, the factor C alpha minus Cs raised to 1 by 2 is small enough to redraft the equation as capital R equal to capital D into small t raised to 1 by 2, which is given as equation 27.5. These equations have been derived for one-dimensional diffusion process. These results have been confirmed by a number of experimental results. The consistency of the factor V into C alpha minus Cs raised to 1 by 2 may be verified by plotting R against T raised to 1 by 2, capital R square against T. The difference in the calculated time period during which the steady state concentration is established and depletion of the available solute destroys the linear nature of the graph. Frank developed equations for growth rates in diffusion control process for different structures. Consideration of the distribution of the growth rates from top to the bottom of the gel column, in which one component diffuses through the gel, charged with the other component. It has been observed that the rate of growth is greatest near to the gel solution interface of the column, where the concentration gradients are high, and less near the bottom, where the concentration gradient is least. It has been observed that the quality of the crystals increases at slow growth rates. Nucleation control in gel method. The most important feature of the gel growth method is its ability to control nucleation. However, it's a very sensitive and crucial aspect of gel technique. The diffusion rate can be controlled in this technique to a very great extent, but it is not enough to control the population of nucleation centers in the gel matrix. The lack of knowledge on actual structure of the gel prevents one from taking any effective measures for nucleation control. The commonly used gel methods to minimize the spurious nucleation in gels are: 1. Optimization of gel density. 2. Aging of gel. 3. Concentration of nutrients. 4. Stabilization of thermal condition. 5. Use of additives. 6. Use of neutral gel technique. And the next, control over factors that affect pore size of gel like pH, gel age, etc. Control on gel density yields good results. Gel specific gravity in the range 1.03 to 1.06 grams per cc has been found to yield good results. On increasing the gel age, the size of pores gets reduced, which leads to reduced number of nucleation centers. Use of neutral gel technique is also a method which helps in controlling the nucleation centers. Programming the temperature of the gel medium enables contraction or expansion of the dimensions of the pores. Manipulation of the concentration of reactants to control nucleation was suggested by H.K. Henisch. The method is to keep the concentration of the outer electrolyte very low, which reduces the nucleation sites. After the establishment of nucleation centers, the concentration of the reactants is enhanced, which enhances the growth. By using additives in a controlled manner, one can reduce the number of nucleation centers by increasing the activation energy for the formation of the nucleus. The application of an electric field for controlling the growth is also a possible option. Methods of crystal growth from gels. The basic techniques of growing crystals from the two salts in a gelatinous medium may be described as follows. Single gel technique. Figure 27.4a is a schematic diagram of single gel technique. In this technique, a solution of one of the reactant salts is incorporated in the acid silicate mixture before gelation occurs. In fact, it supplies the first component of the reaction. A solution of the second salt is then gently poured on the top of the gel after gelation. This solution supplies the second component of the reaction and also prevents the gel from drying out. A slight modification of the above technique is to form a neutral gel over a packet of one of the reactants. A solution of the second salt is then gently poured over the gel medium after regelation occurs. Figure 27.4b illustrates this technique. Figure 27.4 is a schematic diagram which illustrates different growth processes using gel medium, which shows in A, single gel technique using dissolved salt, second, two gel technique using solid salts, C is U-tube technique, and D shows modified two gel technique. U-tube technique. U-tube technique is a slight modification of single gel method. In this method, neutral gel is allowed to be formed in the U-tube as shown in figure 27.4c. The solution of the two salts needed for reaction are poured in the two limbs of the U-tube. These solutions diffuse slowly into the gel medium to produce the required crystals of the bottom base of the U-tube. Two-gel technique. This technique is first explained by the schematic diagram shown in figure 27.4d. A gel containing one of the reactant salts is placed in the bottom of the test tube. A second gel, called neutral gel or the reaction gel, is formed over the first gel. A solution of the second salt is then poured over this neutral gel. For the formation of crystals, cations and anions must diffuse through the neutral gel and come in contact for reaction and accompanying supersaturation and precipitation to occur. Modified technique. In order to suit the requirements of growth for some specific materials as well as to improve upon the existing techniques for obtaining larger and better quality crystals, the basic techniques were modified. One of the modifications includes hybrid gel technique, which was used by Arendt and Huber in 1972 for the first time for growth of the crystals of Ag2H3IO6. The apparatus is shown in figure 27.5. The main components of this setup are two small U-tubes containing gel columns which are joined with one end to a burette and with the other one to a thermostated double-walled glass vessel containing a stirred growth solution with rotating seed crystals. The basic as well as modified techniques have been described by Henisch in his research articles and also in his book Crystals in Gels and Lagrange Rings, published by the Cambridge University Press in 1988. Figure 27.5 shows a schematic diagram in which the apparatus used in hybrid gel technique by Arendt and Huber is shown. Gel helps in establishing a stable pattern of concentration gradient by suppressing convection currents. Gel assumes the role of a three-dimensional crucible which supports the crystal and at the same time allows it to grow further without exerting forces of large magnitude upon it. Gel also suppresses nucleation and thus helps in increasing the size of growing crystals. Gel can be regarded as loosely interlinked polymer as they are formed from suspensions or solutions by establishing a three-dimensional system of cross linkages between the molecules of one component. Advantages of gel method. Some important advantages of gel technique over the other crystal growth methods are: number one, silica gel being optically transparent, crystals can be observed in all stages of growth. It helps in the studies on growth kinetics and in making in situ observations. From the thermodynamic considerations, it is known that crystal grows at low temperatures are expected to have lower concentration of equilibrium number of defects than those grown at elevated temperatures. Gel growth being a low temperature solution growth, it finds application in the growth of crystals with fewer defects. All early formed crystal nuclei are delicately held in the position of their formation, thus limiting effects due to impact on the walls and bottom of the container. All nuclei are spatially separated, minimizing any effect due to precipitate interactions. The procedure itself tends to mass production and is very economical since elaborate apparatus is not required. The gel medium remaining chemically inert and harmless, the gel frameworks act like a three-dimensional crucible in which the crystals are delicately held in the position of their formation and growth, thereby preventing any damage to the impact with either the bottom or the walls of the container. It forms three-dimensional structure by entrapping water. The gel, being soft and porous, provides a flexible environment for crystals to grow. Now we shall know about the limitations of gel method. The gel method of crystal growth has certain limitations which may be summarized as follows. The gel method restricts the size of a crystal. Larger crystals are difficult to grow. There is a considerable amount of possibility that appreciable amounts of impurities may go into the growing crystal lattice. Examples of gel-grown crystals. Numerous crystals have been grown by using gel encapsulation techniques. A few examples have already been cited. However, some of the crystals grown by gel technique may be shown here. Figure 27.6AB shows superlytic, twinned, and single crystals of mixed gadolinium barium molybdate crystals as grown by single gel, single tube technique using the system GdCl3, that is gadolinium chloride, plus BaCl2, that is barium chloride, NH4NO3 Na2SiO3. Figure 27.6 AB are the optical micrographs which show superlytic twinned and single crystals of mixed GD-Ba molybdate as grown by single gel, single tube technique. Figure 27.7 shows single and twinned crystals of gadolinium barium molybdate as seen under the scanning electron microscope. Single crystals of ytterbium tartrate as grown by using single gel, single tube technique using ytterbium nitrate as the upper reactant and tartaric acid as the lower reactant and agar-agar as the gel medium are shown in an optical micrograph of figure 27.8. Single crystals of gadolinium tartrate trihydrate as grown by using gadolinium nitrate and tartaric acid incorporated in agar-agar gel is shown in figure 27.9. The gel technique of crystal growth has proved of great use in producing samples of crystals for research purposes, especially for laboratories with limited facilities of crystal growth. Here in figure 27.8 is an optical micrograph of single crystals of ytterbium tartrate grown by using agar-agar gel. And figure 27.9 showing single crystals of gadolinium tartrate trihydrate grown by using agar-agar gel. So students, let us summarize what we have learned in this module. We have learned about crystal growth by gel encapsulation method. The structure and properties of gel have been explained. Mechanism involved in the gelling process that makes it effective in the crystal growth process is discussed. Various techniques of growth by gel method, including growth by chemical reaction, chemical reduction method, complex decomposition method, and solubility reduction method, as may be applicable for the growth of some specific crystals, are described. Growth mechanism in gel and nucleation control in gel methods has been explained. Various methods used for growing crystals using gel as medium of growth are described. Advantages and limitations in using gel as medium of growth has been explained. Some examples of crystals grown by gel method have also been given with details. Thank you.